Hello, this is Jeff, and this is episode number 2 of our C tutorial and building Donkey Kong using nothing but C11 and SDL2. Yesterday, I went through some of the introductory stuff with C, types, functions, modules, static, prototypes, header files, and some pointers. I received some feedback, and some folks would like me to focus some more on pointers, const, and static. And so before we go into that, I just want to kind of get you up to date on what I've done with the project. I couldn't help myself. I got so excited yesterday after making the video. It was so much fun to write C again, which I know it sounds probably silly, but so in the string header, or in the module, let's talk about the string stuff real quick. I added a new field to the string structure called pos. So we have a string, it has a length, it has a pointer to a buffer on the heap, and pos represents how much has been used out of that length. That allows us to do an append, and I went through and I tidied up some of the prototypes on this, some of the names, and made sure that in the cases where I'm not modifying the pointer, the string structure, I pass it constant. We're going to talk about that in a little bit more detail. I added stir print C, which will allow us to print just a character to a file, open file handle. And I added append Z and append. Append Z will append a null terminated string. Append will append another string structure to an existing string structure. And so then if we, excuse me, go into the implementation file, someone did mention that I had forgotten to add freeing the data buffer back in, so I fixed that. And, excuse me. And then, that's right. So then some of these other functions, instead of repeating this kind of boilerplate, creating the string structure, checking for null, calling abort, allocating the buffer, most of these other functions now defer to stir new. So we kind of get some code reuse there. But you can see, like in stir clone, before we were doing a stir dupe. We're not doing a stir dupe anymore. Now we're doing a stir new to get the buffer, to get the structure in the buffer, passing in the length of the string that we're trying to clone. Then we just do a mem copy, and then we set pos to length because we've populated the entire buffer. So if we wanted to append to this buffer, it would have to reallocate the buffer. Strlen, I think I just made this const. Stir print C is pretty straightforward. Pass in a char, pass in a file pointer, assert that the file pointer is not null, and then we use fwrite. And then string print below it. Well, this is what we had yesterday. If you remember, we had that buffer, we had that static buffer. So I got rid of that buffer. We don't need it anymore. Now I just do an fwrite to the file handle that's passed in. This is the pointer to our data. This is the size. This is the size of the unit of that data, right? So we're printing characters, so they're 8-bit values, and then this is the number of units. So it's this times that. That's how many bytes are going to get written to the stream. And this is our file handle. And so this eliminates the need for that buffer. No more fprintf, no more buffer. And for printing a single character, we pass in the character. You'll notice I'm taking the address of the character because fwrite needs a pointer to the buffer where it's going to read from. And I'm going to do some going to cover these things a little bit more detail here in a sec. I just wanted to kind of get everybody up to speed on what I've been doing here in my my crazy lab with my crazy scientist dreams here. So the size of the unit is a character. We're going to do one of them, and we're right to that file. And again, the rest of these are just refactored to use stir new, and we have append and append null terminated string. I haven't tested those yet. We'll probably get to that. So that's on the string front. Then we have, so if you remember, I did, for a week, 6 days, I did CKong. And I had gotten quite far with the CKong implementation, I think anyway. I mean, I got tools built to rip tiles and tile maps and palettes and all that good stuff. It was all in Rust. And I didn't really see much point in rewriting the tools. In this case, they do what they're supposed to do. So I just, last night I copied all the data over and reformatted it so it's C compatible. So we have a palette module, a sprite module, a tile module, and a tile map module. So we're going to go through these real quick. In the header files, I have a constant for the max number of palettes, which is 64. The Donkey Kong hardware had 64 4-color palettes. A palette entry is just red, green, blue, alpha. Those are all bytes. A palette consists of 4 entries. And then if we look at the module, we have a static S palettes that is an array. We didn't cover arrays yesterday. I'm going to do that today. We're going to talk about those some more. And then this was Rust code that I just reformatted with some text functions in the editor so that they would initialize the C structures. So the way to read this is, this initializes the array, this initializes the palette structure, and this initializes the array inside the palette structure, right? So we have an array here. And then this is each entry in the array, which is a palette entry, which has these values. And there are 64 of these. Okay. It's static because we're going to have functions that help us get access to things inside of this palette, right? We'll return back a pointer to a palette T by indexing into this. But this will give an idea, once we get into this some more, of how you can hide things in C. Tile is very similar. I have constant values here for the tile width, the tile height, and the max number of tiles. So the Donkey Kong hardware tile is 8 pixels by 8 pixels, and there's 256 of them in memory. The structure is very simple. Right, for a tile bitmap, it's just an array of bytes, tile height times tile width. And then if we look at the module, we have, again, a static array of tile max. So there's 256 of these. And these are the palette indexes that would give us the color information for that tile. Right? And again, this initializes this array. This initializes this array here. So that's how that works. And then we have sprite, which is again almost identical to tile. We have width and height, we have the max number, we have our structure, which has the data array in it, which is height times width. Right, so 16 times 16, it's 256 bytes, right? Yep. So if we look at the module, it's the same thing. Just arrays of bytes that populate those structures. And that's it. And then tile map. So a tile map is metadata that describes what tile goes in which position to fill out the grid, right, on the screen. The Donkey Kong hardware, the resolution is 256 pixels by 256 pixels. So there's 32 by 32 tiles on a screen. A tile map entry is the tile number, the palette, and the flags. This is the palette index. And then flags, I need to put some enums in here for those. But flags are things like flip horizontally, flip vertically, things like that. And in the module, I just pulled over the data and restructured it so that it populates the data the way we want. And that's it for those. And then, so you can see I replaced the fprintf with strprint C. There's still one fprintf in here for debugging purposes. So what we're going to do is I'm going to copy test str module. I'm going to copy this stuff and put it in here. And then that, we won't lose that code, our little test code there. But it allows me to do some other things inside of main here without getting the noise from the string stuff. Okay, so let's talk about, what should we talk about first? Let's talk about const. So const is really just, especially in C, I wouldn't overcomplicate it. I'm going to look it up in the spec here. C11 const definition. Const type qualifier. Each individual type in the C type system has several qualified versions of that type. The corresponding to one, two, or all three of the const, volatile, and for pointers restrict qualifiers. So const semantics apply to L value, so we'll talk about that here in a sec. Whenever a const L value expression is used in the context that does not require an L value, its const qualifier is lost. And then there's stuff here about volatile, which we're not going to talk about today. L value expressions that designate objects of const qualified type, and the L value expressions that designate objects of struct or union type with at least one member of const qualified type are not modifiable L values. In particular, they are not assignable. So the short of it is const means read only. That's the way you should interpret it. And that's how you should think of using it. Okay. So let's take some examples. All right. So first, let's do an int, signed int 8-bit integer, and we'll call it foo. And we're going to make this equal to -64. And just for debugging purposes, I'm going to use printf here. So foo is equal to this, right? So let's run that. And we get -64. Okay. Now, what happens if I change foo? So foo is mutable, meaning it's writable, it's changeable. So let's say I change it to +64 and I print it again. So now we should get two lines, well, two sections. Let's put a line break after these. So there you go, -64, 64. Now what happens if I put const here? Well, C-line already, the IDE I'm using already recognizes, hey, you can't do this. But let's compile it and let's see what the compiler says. You cannot assign to a variable foo with const qualified type const int 8t. Okay, so what does that say? What does that mean? Well, this is just C speak for this is read only. Now, you can't, once you've set it, you can't change it. Okay. So now this also can apply to pointers. So let's take an example there. So you can see here how you could create a constant integer value. There's a read-only integer value, okay? And this applies to char, float, double, any of the intrinsic types. You can do this. Okay? So let's make a pointer to something. Let's make it const, okay? So let's do a uint8t pointer, call it buffer, and we'll call malloc, and we'll allocate 256 bytes, okay? And then down here, I'm going to free it. I'm not doing error handling code for this. This is just to help you kind of learn how these things work, okay? So now I have a non-const pointer to 256 bytes on the heap. Okay, so let's say that I then change the first byte, which is at array index 0. Now let's talk about, I'm going to come back to the array stuff, okay? Because this is the same as this. We're going to talk about that. But I'm going to just make the 0th entry in the buffer equal to A, the first equal to B, and the second equal to C. Okay? And this should be fine, right? This should run and nothing happens, right? And if we put a breakpoint here before we could do the free, we should be able to look at our buffer, and sure enough, A, B, C. Okay? Now, and so far we haven't done anything here other than indexing this as an array, or I should say using the array syntax to index into it, than we did yesterday with the string stuff. It's the same thing. Nothing's changed. Now, what if I do a const uint8t pointer read only buffer, and I assign buffer to it? Now what happens if I do read only buffer and 4? I can't do that. Let's try to compile that. Read only variable is not assignable. Now it's interesting the error message is different, but it's the same error message, okay? At the end of the day, const means read only. You could create a type def or a pound define for this in the preprocessor. You could do pound define, read only const. It's the same thing. That's the purpose that it serves. Now, why would you care? Well, of course, there's design reasons why you would want to do this, why you would want to use const, and there are some compilation level reasons why you might want to use const. So by making something const, you are providing the compiler with more information. You are telling the compiler, hey, in this case, this pointer, nothing can write to memory from this. Now, I could read from memory. So slot 2, I could read from read-only buffer 2. Then I could do printf slot 2, right? And there's our character C. Okay, so you can read, of course, it's read only, but what we're doing here is we're telling the compiler, hey, this, when you see this, and any code that references this type, this variable, don't worry about mutability, don't worry about things changing. I can only read from it. So again, it gives the compiler some additional context where it could potentially optimize some things for you. Because it knows this is, again, like, Rust has kind of the similar idea with the borrow checker, right? Because it's so strict in enforcing what you can borrow, what you can't, it knows that down the line, down the chain, things are either completely immutable or they're mutable, and therefore it has to be prepared for those kinds of scenarios. Well, the C compiler is kind of the same, right? It's not as fancy, but basically by marking this variable as read-only, the compiler knows that this can't ever do any writes to memory. So that's const in C. Now again, I encourage you to read the documentation because, there's details on a lot of this stuff, right? So as an example, we can have structs that have const fields in them too, right? We have unions that have const fields in them. So, you can get complicated with what's read-only in your implementation, but the concept is read-only. So that's const. And hopefully that gives you a little bit better understanding of what's going on there. So if we look at the string module again, right, where I'm passing const char, right, I can read from this pointer. I cannot update it. Same thing here. I'm appending this strt pointer, the contents of this structure, I'm appending. By marking it const, if I tried to update that pointer, if I tried to update that that pointer, basically, I try to stomp on it, the compiler is going to see, no, that's read-only, you can't do that. So that's what that's getting you. Okay. I think the other one was static. And I'm going to look up static here, just so I have the lawyer definition of language for static. So let's see, C11 static definition. Okay, so static duration storage class specifier with internal linkage at file scope and no linkage at block scope. What the hell does that mean? Okay, that's the definition as it's written out on CPP reference. So okay, static duration storage class specifier. What does that mean? Here's the thing. Again, I encourage you to read the documentation. You can get all the minutia and detail on a lot of these, and at some point you probably will want to know what all the details are. But for beginner purposes, for learning purposes, don't get too wrapped up in all the complexity because it's just going to confuse you. Here's what you need to know about static. Again, const, read-only. That's the way you should think of it. Are there more details there? Yes, read the documentation. And as we come across, scenarios where we're getting into the more fine-grained aspects of something, I'll talk about it. But if I throw like the entire spec at you, you're going to get confused, and that's no fun. So, static. What does it mean? All you have to know with static is that static means module. It means this belongs to this compilation unit. And you're by static, and static is a weird word. And the reason that this is the word static is because, without getting into a lot of esoteria, at the linker level, inside of the object file, there are sections that are called static. And that's why the word static is used, because this ties directly to why they use the word linkage. This ties to the linkage process, where the linker is taking all these compilation units and combining them together. And the linker knows that things that are in the static section belong to that module only, right? And there's initialization rules around static specifically, right, because of the nature of how that data is stored. So, in static data, just so you know, static things, those are, they're copied, you know, into the output, right? So all this static data that I put in my modules here, because this is static, this is dumped into the object file, and it's a part of that permanently, right? So the way to think of static is, or a good analogy for static that you can think of, again, without getting into all the nitty-gritty details of what's you know, why does the object file have that section and what's the linker doing with it, you can eventually get to those levels of detail. The best way to think of static is private to the module, right? So if I have a static variable called foo belongs to the main, it will belong to the main object file that is created. It will be in a special section in that object file, and other object files cannot access that data. This belongs to this module and this module alone. Likewise, that whole blurb of, you know, file only and not block level, what that means is that if I put static here, this is equivalent to having put it here. The compiler will see static declarations, and it knows that a static declaration is file level, module level. It's not block level. So even though I might have several basic blocks and I might put statics inside of them, those get hoisted right to the top. So static, whether it's data or it's a function, it's irrelevant. It's private to the module where it's defined. Okay? Now, by convention, I typically put an S under bar in front of my statics, just so that I can remember what they are. Kind of like, you know, if I had a lot of global variables, I would probably have G under bar, right, to track those. So that's static. It's really no more complex than that. Private to the module. That's all you have to remember. That means that main could have a static foo, tile C could have a static foo, tile map C could have a static foo, right? They could each have their own foo because it's private to the module. And again, data or function, doesn't matter. They work the same way. Now again, there's more detail there, but I don't, you know, I could spend hours just talking about this one topic, right? So I think you can write a lot of effective code just, again, with the analogy of if you want to hide something, if you want something to belong to a module, so think of it like a global variable or a global function that can only be accessed within the module, right? That's its scope. It doesn't go beyond that. You can't link to it somewhere else. So if you had a bunch of functions, again, remember we had that buffer in the stir module. You have a bunch of functions that need to refer to something common at the module level, static is the way to go. Now, if you have a bunch of modules that need to refer to something, that's global, and we'll get to global later. We're already kind of doing globals. We have global functions, right? But global data is a bit different, so we'll get to that down the road. If needed, you may not even need it, right? I prefer to use static state, right, in a module, and have global functions that manipulate that state versus having a bunch of global variables that are exposed. So now let's talk about arrays. We didn't talk about arrays yesterday. So let's have a uint8t array. Uint8t foo, and we're going to do 32. Okay. So, all right, what is this doing? And this is allocating on the stack. And that's the other thing. We haven't talked really about the stack too much. So this is allocating 32 bytes on the stack. So for those of you who have watched my assembly language videos, this would be the equivalent of, sub RSP 32, right, in assembly language. We're taking the stack pointer always grows down, and the compiler is making room on the stack for 32 bytes of data. If these were integers, if these are 32 bit integers, let's say, so what we could think of as an int, right? This is 4 times 32, right? Because this is a 4 byte value times the number of entries in the array. So again, similar to the way pointers work, the type designates the size of an entry in the array. So uint8t, this is exactly 32 bytes of data. Now, I'm going to confuse you. uint8t pointer foo is equal to the address of foo 0. So what's going on here? Well, this is the same as a pointer for all intents and purposes. It's just a different syntactical presentation, okay? So I'm going to comment this out for a second, and let's write a loop for uint8t I is less than 32, increment I, foo I equal I. Okay, so now if we put a breakpoint here, run this in the debugger, what do we have? So that you'll see the debugger shows that foo is a byte array, 32 bytes in size. Here's the array, right? And you can see that we populated 0 through 31 into the array. Right? Very simple. Now, let's comment this line out. Let's put this line here, and let's go foo p plus plus equals I. And run that through the debugger. Now, look at our array. It's exactly the same thing. Okay? So, how does that work? What's going on there? Right? And why did I put a star here? And what's the plus plus for? Okay. So, what I'm doing, this is the address of operator. It also is the logical AND operator, but when it comes in front of a variable, this is the address of operator in C. In C++, it can also be the reference operator. Don't get those confused. So when you see this in front of something, it means address of. Okay, so now I'm taking the address of the first element of the array because I want to point at the first byte in that array. So this pointer points at the address, has the address Because again, what is a pointer? A pointer is just a number that is the address, right? In fact, if we wanted to, right, let's do this. Let's see, what type does it want me to use? No, I don't want it to be a string. There's probably, I can't remember. Does printf have a specific, let's see, printf pointer address. Correct format specifier. What does the standard say? Ah, P. All right, yes, let's do P. So we're going to run that, and we look at the console. That's interesting. Oh, it didn't flush. Okay. So let's put a line feed in there. We'll run it. Okay, so really big numbers, right? This is what a pointer is. This is all a pointer is. It's just a number. It's a number that represents a slot in memory. And again, at the CPU level, and this is why I encourage folks to learn assembly language, there are addressing modes within the CPU that are able to take a number like that and say, oh, that's in memory. Go to that location in memory and put a piece, put a value there, read a value from that location. In C and in other high-level languages, is a little bit confusing because that's sort of abstracted. This right here means read. This right here means increment the pointer, right? So again, if we look at the output window, notice 0, 1, 2, 3, 4, they're just incrementing by 1. This is where this memory starts. And coincidentally, because I'm taking the address of something that's on the stack, this is pointing at the stack as well. So if we were to, look at this at the assembly language level, if we looked at RSP, we would see that the RSP is pointing at this location, actually, after this is all said and done. So this is called a pointer dereference. Now, there are different ways to dereference a pointer, and this is where things get a little bit confusing, okay? This is one way. So, dereference with star. We can also dereference with array semantics. So, foo p I equal I. So this is valid, the one I just commented out. This is valid. They do the same thing. They're just syntax differences, right? Because again, in C, arrays and pointers are essentially identical. They are the same thing. The only difference is the syntax that you're going to use predominantly. Sometimes it's nicer to think of things with the bracket syntax and passing an index. But all that is, so here's another way to do the same thing. We could say foo p plus I, put that in parentheses just to make it clear, put the star in front of it. actually, I won't do the post increment. We'll do that separate. Equals I. So what's happening here? This is taking the base pointer, just like you would with this syntax here. This is the pointer. This is the index to that pointer, inside of that pointer, being added to the offset of it. This is the same thing. Here's the beginning of the array. Here's the index of the array. This is dereferencing that pointer, because again, remember, pointers are just numbers, and assigning the location in memory that that pointer points to this integer value. Okay? Now I didn't change the pointer, right? So this is one of the nice things about the array syntax. You don't have to worry about adjusting the pointer yourself. By just changing the index, the compiler does that for you. So that's one of the advantages of the array syntax versus just raw pointers. Here, I have to know, well, in this case, I'm duplicating the array behavior, so I don't have to do that. But like here, if I didn't want to do the post increment, right, so that's what this is. This applies to the pointer, not the dereferenced thing, right? So the way to read this line is read the value at foo p, assign I to that memory location, increment foo p. So it's actually, this line's doing three things. So it's kind of interesting, right? But we could take this off, and then we could do foo p plus plus, or what a lot of people prefer, in that case, just use the pre-increment on the pointer, right? And that's equivalent. It's just that you're doing it in two steps in the code versus all of it in one line. But this and this and this and this are all equivalent. They're all the same thing. Now, I'm using bytes here because it makes things a little easier to understand. Obviously, if you had an array of integers, or array of floats or doubles, or an array of a struct, if you have a complex type, then the math becomes more complex, right? Because then it's not just, you're not just moving one byte at a time, you're moving many multiples of bytes at a time in memory. So just keep that in mind. Again, the base type of the array, just like the base type of the pointer, dictates not the size of the pointer type itself, but the size of the data that the pointer dereferences. Okay? Now, hopefully that makes sense on some level. The best thing that I can tell you to do here is to follow what I just did in this video and do it yourself and play with these different variations, right? And use bytes, use a simple scenario so that you understand what's happening. Now, what I would like to do is I would like to talk about the address of operator a bit more, okay? So let's put a char here. We'll call it C, and we'll fill it with an A. Now, this is on the stack. So again, what is a stack thing? What is a heap thing? So in C, it's very straightforward. If it's a type, so one of our base types that we talked about in episode 1, or a pointer. Again, a pointer, the pointer itself is just a number. It has to live somewhere. These things live on the stack. Okay, these numerical values live on the stack. And it's interesting, again, you remember from yesterday, all the types in C are numeric. There is no string type. Strings are, again, blobs of memory that are interpreted a certain way, almost always on the heap, although not exclusively. And why is that? Why are they integer values fundamentally, right? Because again, remember, char is a byte. This is the same as that. So Well, think about it. C, again, is just one level above assembly language. And fundamentally, what you can put on the stack are numbers. That's what the CPU understands. What you can put into a register is a number. That's what a CPU understands. A CPU, again, depending on the CPU on your platform, it's going to understand bytes, shorts. Technically, it's going to understand bytes and words, whatever the word size is for your platform. And it might understand half words, double words, quad words, right? Just the different size of word, right? That the CPU register is able to comprehend. And so C maps very, very cleanly, although the names are weird, to what your CPU has to offer in terms of its core functionality. Okay, so again, what is a stack? Let's do some ASCII art. A stack is a pointer, so let's call it SP, and let's just say, for the sake of argument, that it's pointing at address 4000, which is for oh man, I just whiffed. I have no idea what I was going to say. I was going to say something about that. Oh, 16K. That's what I was going to say. Right. So this is 16K. This is the equivalent of, what was it again? $16,384. Right? This is an address. Okay? So if what's our pointer type on the 64-bit platform? It's an 8-byte integer. So this is probably uint 64T, right? So it's a 64-bit value that has a number in it. That's it. It's just a number. So in memory, okay, this is what we call the top of the stack, okay? So how does the stack grow? The stack grows down. I don't really have anything that goes down here. Right? So the stack goes in this direction. Right? So that means the stack pointer starts at 4000 hex. Again, this is an example. This is not what's actually happening on your machine. This is just an example. And if it's a 64-bit machine, that means that each entry in the stack is 8 bytes. Right? So this is 8 bytes, 8 bytes, right? Because every time you dereference the stack, it's based on the size of the default pointer on your platform. Most of us are on a 64-bit machine, 64 bits, two 32-bit integers, 8 bytes. So the stack grows down, and this is an entry, this is an entry, this is an entry, this is an entry, right? So, so actually, I guess technically, you would call this the bottom, right? Sorry. And then this would be current top, right? Okay. So in C, what happens here is we define a byte. Well, now this is interesting, right? I just said that the entries in the stack are probably 8 bytes in size, and they are. So what ends up happening is you have a 64-bit value on the stack, and if you look at it in memory, the last 8 bits are the only bits that are being set in this case. So you have a lot of bits that aren't being used. This is an important thing to note. So when people talk about cache line utilization and performance and things like that, these are things you have to keep in the back of your mind. If your architecture is chunking things up in 8-byte increments and you're passing a single byte around, you might be wasting a lot of bytes that are going unused. So just something to keep in the back of your mind. So space is made on the stack, and this value is put into the stack frame, okay? Now, the stack is in memory, right? It's just like every other piece of memory. It's just that the stack is controlled by the CPU, and you could consider it a special range of memory because there are special instructions in the CPU that deal with the stack, and the C compiler is designed around those conventions, okay? So now, within the scope of a block, so let's do this. Let's create an anonymous block, and let's create another value like this, okay? What's happening here? Well, this is another scope, and when this scope ends, foo should be gone. And it is, right? There is no foo here. If I put a breakpoint inside of that block, I should see my foo, right? Now the compiler is probably optimizing stuff out of the way here, but so let's do this. Let's do a printf here. So the compiler has to keep it around. Right, so there's foo. Boom, you saw it show up. We printed it, but now look, foo's gone. What happened to it? Well, it got popped off the stack, right? Every scope here, whether it's an anonymous block or a block tied to an if statement or a while loop or whatever, if you have a block, that creates a new frame, a new scope. Auto variables, things that live on the stack, have a duration of that scope. So when we fall out of this scope, this is deleted. This is freed automatically. We don't have to do anything special about it because it's on the stack, and the stack is designed to work that way. Things get pushed on, things get popped off, right? Now, what if we have a stack thing? What if we had this 1 byte here, and we have another function. Let's create another function. Let's call it frobas, okay? And frobas is going to take an int 8 pointer called p, and it's going to dereference that pointer and assign the character f, uppercase F, to it, okay? So I have this thing on the stack. Now if I try to call frobas and just pass C, C-lion's like, well, maybe. It didn't like flat out say it's an error, but it did highlight it yellow. Now it's be interesting, what is, see, C-lion's suggesting, that the thing that you're calling, it wants a pointer. So maybe you need to cast this. Now the thing is though, the cast is not really right. That's, if you were to accept that at face value, that wouldn't work. Because casting the letter A to a pointer is not what you want to have happen. What you want is you want the address of that stack thing. Because again, this lives in memory. It's there, it's allocated. While it's in scope, it's valid, okay? So by using the address of operator, I can turn this into something that's castable to a pointer, Right? Again, this, if we were to do this, if we were to do a printf address of C is equal to %p, and take the address of C, and we won't call throwbas yet. Oh no, this is just printf, I think, being silly. So there's the address of the variable C on the stack, okay? So then if we call throwbas, there you go. We take the address of C, which can be assigned to a pointer that works, that number. This is a number type. This is a numeric thing, which would be 64 bits, very big number, right, on this platform. And that can be passed into this pointer. And with the address in the pointer, it has a base type of byte. I can then dereference the byte and assign a value to it. So this is writing the letter F into memory at that byte location. So that's the address of operator. That's how that works. And you can take the address of anything that's on the stack and you can pass it around. The only rule that you have to follow is, again, you don't want to pass the address of something that's gone. So as you saw earlier when I had that private scope, if you have something that only is alive within a scope and then you later try to take the address of it, bad things are going to happen. So just keep that in mind. That's your limitation. So now, interestingly enough, our main method at some point is going to call some, do the game method, do the game function, right? And this thing is going to block. It's going to loop. So if we had a bunch of things on the stack here and we pass the address into this, they'd be valid because this block has not exited yet. So that's another thing to keep in mind. You don't always have to allocate everything on the heap. Sometimes you can allocate objects on the stack and pass the addresses around as if they were pointers, but in reality they live on the stack and they always will be on the stack. Again, the nice thing about putting things on the stack is that memory allocation is handled for you automatically. When things go out of scope, those autos, they get deleted because the stack frame is unwound and they go away. And obviously the stack is also used for return values from functions. It's used for the return address, right, for functions, so things can be recursive and all that good stuff. Okay, so that covers, we talked about the stack, we talked about pointers, we talked about arrays, we talked about the fact that arrays and pointers are kind of two sides of the same coin. We talked about const, we talked about static. I'm sure, again, folks will have additional questions about that stuff, but let me know in the comments on the video or on the stream, and I will certainly try to cover any areas where things are still not clear. So let's do one more thing towards our project here. I think for now our string stuff is okay. And I got data in here for the graphics. So what I would like to do is let's create a module and let's call it actor. And our actor module is going to in the header file, we're going to have a struct, right? Actually, a couple structs. So let's start with the obvious one first. So type def struct actor t, and an actor has a bunch of stuff on it, right? So he has let's include standard int. So we have our nice type defs here. So we're going to use a 16-bit integer to represent x, a 16-bit integer to represent y. We're going to we'll use a 8-bit integer to represent the current frame. And we probably have flags, right? So what's it complaining about? Oh, gotta do the type def. And for now, we'll just have none. But we'll have some other flags. So we have the position, we have the frame in the animation that the actor is, some flags for the actor. And actually, let's do, no. Here's what we'll do. We'll have two 16-bit values, data 1, data 2. So this is our user data, right? So that's 4 bytes or two 16-bit numbers that we can put stuff in for user data. And okay. Now we need frame information, right? So actually, sorry, let's do this. We need something called actor animation. Okay, and an actor animation has frame count, and since we know that it's a so here's where we can kind of balance a little bit between allocating memory and then just having memory pre-allocated in the structure, right? So kind of similar to how we would do it maybe in assembly language. It's a trade-off. So let's make this shorter. Let's just call this an animation T. So then our actor is going to have an animation T pointer that points at the animation, and we'll have a delay value for our timing on the animation. And then we have an animation frame. So here, because we're using a 256 byte, we're using an 8-bit value for the frame count. We can have up to 256 frames for an animation. So then the question is, okay, so if we do an array, animation frame T frames, 256. Right. So we're pre-allocating a block of frames. We might have wasted space. That's the downside to this. The upside is we don't have to have all these pointers all the way down the structure that we have to manually manage ourselves. So then what is an animation frame? An animation frame is a uint 16t x offset, uint 16t y offset, uint 16t tile, uint 16t flags. So actually, sorry, I'm going to move the delay there. This is animation frame tile, animation frame tile T. So these come up here. We have a delay for the frame. Then we have an array of animation frame tile T tiles. And again, we're going to have a uint 8t tile count. So we know the max is 256, right? Because this value can only go up to 0 to 255, right? Is what we can have. The size is 1 based, right? So we can have 256 tiles within a frame. So this, we're going to have some extra memory, right? So if we multiply this out, right? So what's the size of an animation frame T? It's 2 bytes plus 1. There's going to be padding in here. The C compiler takes care of padding for us. And then we have an array of tiles. What's a tile? This is 2, 4, 6, 8 bytes, and it may have some padding in it, right? So 8 times 256, so it's 2K per frame, and so 2048 times 256, so half a megabyte is roughly what an animation costs us if we do it this way. Now, obviously, none of our animations are going to have 256 frames in them, or 256 tiles. So we could probably, like, I think when I was doing Timber, right, on the Raspberry Pi, I think the largest animation I had was like 10 frames. For Donkey Kong, certainly we're not going to have any more than, say, probably 32 frames. So we can limit this to 32. Same thing with tiles. Donkey Kong, I think, is 4 tiles. So if we limited this to 32 tiles per frame, that's probably plenty, right? And so then if we do the math on that, an animation is the delay, so that's 2 bytes, 3 bytes, probably going to be 4 with padding, maybe more. Again, I'm ignoring padding here. And then we have 32, so 32 times 8, that's 256, much better. So 256 times 32, that's 8K. So one animation costs us 8K of memory. Now, again, so this is a trade-off, and the reason I'm talking about this and I'm going through this because this is, the sort of trade-offs you might make in C for simplicity reasons, right? It's easier to put a fixed length array like this inside of a structure, especially if you kind of know what your bounds are. It gets you a couple things. One, this is all nice and tightly packed, roughly. Again, minus whatever padding the compiler might put in for us, each frame here is going to be right next to each other in memory. Each frame tile is going to be right next to each other in memory. This kind of a structure layout, this is when people talk about like SOA, or although this is not specifically SOA, but data oriented and cache friendly, right, is what I should say. This is going to be slightly more cache friendly, because if this were a pointer and this were a pointer, you know, now you're chasing pointers. And so we're allocating different chunks of memory in the heap, and we have to chase those pointers around in the heap. And there's no guarantee that things are going to be contiguous where we want them to be. So those are things to keep in mind when you're doing stuff like this. Again, with assembly language, in the back of your mind, this stuff becomes a little bit more obvious as you're doing it. Okay, so we have an actor. An actor has an X and a Y position. It has a frame, current frame. It has some user data. It has some flags. And it has a pointer to an animation. And an animation has a frame count, right? So we have to manually set the frame count so that we know how many out of the 32 there are that we should use. An animation frame has a delay, so this is in milliseconds. This will be our timer delay. So in between frames, we can change how long we wait to go to the next frame. This is the number of tiles that this frame consists of, right? So again, if you remember how this roughly works, we have these tiles, these bright tiles, and some characters like Donkey Kong are made up of 4 or 6 tiles, and to do the animation, right, we have to set the tiles out in a little grid, and this is what allows us to do that. So each tile in the animation frame has an X and a Y offset from the actor's X and Y, right? So you can go negative, you can go positive. Oh, and that's an interesting bit. So these should be signed. Let's make these signed. And also, I'm going to make the X and the Y on the actor signed too, and I'll explain why later. This is so that we can do clipping easily on the edges of the screen. So we have an X and a Y offset around the actor's hotspot. We have the tile that we're going to use. Oh, we need the palette. And then the flags. And eventually, no, I'm going to leave it that way for now. That'll be fine. This probably only needs to be a byte though. So we ended up with 2, 4, 6, 8 bytes. Yeah, so we still have 8 bytes for a frame tile. So that's fine. Okay. And again, if you followed me doing this in assembly language with other stuff, MS-DOS or ARM, you'll notice this is very similar. It ends up being really, really similar. So, all right. I would like to try to aim to keep these videos right around an hour. So I think we're close to that today. This is what I wanted to kind of flesh out. And then tomorrow, the next video, we'll pick up and do some more stuff. I'm probably going to play with this some more because I'm actually having fun playing with it. So our next steps, roughly, are then to start implementing the actor stuff so we can allocate an actor, defining the actors, having the actor update function, and then we need to do a state machine. And when we do the state machine, we'll get into pointers to functions, which are pretty straightforward. The syntax is bizarre, but once you get past the syntax, it's, you know, easy peasy. And yeah, and so we'll get the state machine set up, and then once we get those pieces in place, then I think we'll set up some SDL stuff in main, and we'll actually get the probably what we should do is we'll have a game module, right? And so main will just really call game, and game will set up, you know, the window, and we'll set up, you know, all the stuff it needs, and then start using the state machine and all that good stuff. So anyhow, that's I think that's a good stopping point for this video. And again, let me just say a couple parting words here. I'm going, actually, let me do this. Let's review this real quick. So we added actor C, nothing in there yet. In our header file, we defined our structs. I'm sure this compiles. No, maybe not. Oh, got C++ on the brain. Okay, so we have our actor structures for animation and everything. Added in the actor module to the CMake lists file. In main, I shifted our string test code up into tester module, and we're going to keep that there. We'll continuously kind of tidy this stuff up as we go along. And then in string, I added, looks like one line to be consistent there. So let me I'm going to push that up so you guys can see that code. So if you enjoyed the video here on YouTube, please like, share it with folks if you think they would like it. Subscribe. I would greatly appreciate that. If you want to join us any day, Monday through Saturday, for my Twitch stream, I run that from 5 a.m. to 10 a.m. Mountain Time, Monday through Saturday. That's at twitch.tv/nybbles.io, NYBBLESIO. And if you have questions, or if something I've covered doesn't make sense, or there's an area that you would like me to talk some more about, by all means, add a comment. And I'm trying to, read all the comments and follow up and try to incorporate areas that folks have questions about into the video series. So in terms of the basics of C, I mean, again, believe it or not, we've really covered it. C does not have a huge surface area. Now, again, there's lots of esoteria. I don't want to, in the common case, in the general case, what I just said is applicable, right? There's always special cases. There's always complexity that you can find. You can dig up problems if you look for them. But for a lot of what folks want to write code for, the foundation that we've covered so far is really, that's the foundation. So I think, I'll incorporate areas for review if people ask specifically about them. Otherwise, I'm just going to kind of keep going forward with the game, and we're just going to keep building stuff, right? And I'm sure as I do that, things will come up and people will have questions, and we can address those then. Anyway, thanks for watching, and I will have another one of these tomorrow. So episode 3 will be May the 3rd. It matches. Perfect. All right. Have a good day, and I'll see everybody in the next video.